there are 6 addition formulae. I'm not going to prove them. What I am going to do is start with one of them and derive a second one. Then I'm going to take another one as given and derive a second one from that. And then we're going to use those 4 to help us derive the final 2. So, this is the one we're going to start with. The sine of A plus B. This is where they get their name from, addition formulae, because here we have a sum and we're going to find its sine. This breaks down as sine A cos B plus cos A sine B. Notice in terms of remembering it, we keep the A and the B in the same order and the sines and the cosines alternate. So, what about the sine of A minus B? Well, let's just have a think about this minus B. It can be the sine of A plus minus B. And now, the formula that we had here can be exactly the same as for this one, but in this one we can replace B by minus B. So let's do that. Sine A cos of minus B plus cos A sine of minus B. Well, the sine A is okay, and the cos of minus B is just cos B. The cos A is okay, but the sine of minus B is minus sine B. So that's going to change that plus sign into a minus sign, and I can just write sine B at the end. So that's the second of our addition formulae. If we've got these for sine, it seems reasonable to expect that we'll have the same things for cos, for cosine. So let's have a look. Cos of A plus B. Well, this is cos A cos B minus sine A sine B. And that's our starting one. So let's do the same as we did here. Cos of A minus B. We'll rewrite the minus B as A plus minus B. And then we can replace the B's in here, in this first formula, with the minus B there. So we'll have cos A, cos of minus B, minus sine A, sine of minus B. Now the cos of minus B is just cos B, so we have cos A, cos B, and then we have minus sine A times by sine of minus B. But the sine of minus B is minus sine B, so we have 2 minus signs together giving us a plus sign. Plus sine A, sine B. So we've now got 4 addition formulae. Let me turn over and write those down as a group. Sine of A plus B is sine A cos B plus cos A sine B. The sine of A minus B is sine A cos B minus cos A sine B. the cos of A plus B is cos A cos B minus sine A sine B. And the cos of A minus B is cos A cos B plus sine A sine B. So there are our 4 addition formulae. Now, we did promise 6, but these are the 4 really basic ones, and really these are the 4 that you've got to learn. The other 2 will presumably be tangent, tan of A plus B. Well, we can derive these from the others. Tan is sine over cos. So we have the sine of A plus B divided by the cos of A plus B. So we can now make the replacement for sine of A plus B by its expansion here, and cos of A plus B by its expansion here. Sine A cos B plus cos A sine B all over cos A cos B minus sine A sine B. Now this looks very unwieldy, and it would be nice if, in the same way that this is in terms of sines and causes, and this one's in terms of sines and causes, I could have tan of A plus B somehow in terms of tangent and possibly cotangent, but certainly I want to have some tangents in there. So what can I do? Well, look at this term here, cos A cos B. Supposing I divided everything by that term, cos A cos B. Well, that would give me 1 here. And I'd have this over cos A cos B. But of course I'd have sine over cos for each of A and B. So I'd have tan A, tan B there. Would I get anything nice on the top? Well, let's write it down in full. So we're going to divide everything by cos A cos B. And I have to divide everything by this because I've got a pair of equal signs here, a balance. So what I do to one side, I must do the other. I must do everything to all of the terms to preserve the equality. Now that looks absolutely awful, absolute massive algebra. So how can we make it any simpler? Well, let's just go back to the denominator here, this bottom term. Cos A over cos A cancels down. Cos B over cos B cancels down. This is just 1. Sine A over cos A is tan A, and sine B over cos B is tan B. So this is just tan A, tan B. Have a look at this. Well, there's a common factor on top and bottom here of cos B. I can cancel that out. Leaves me with sine A over cos A, tan A. Here, the cos A's go out. Sine B over cos B leaves me with tan B. So, what we end up with, the tan of A plus B is tan A plus tan B all over 1 minus tan A tan B. Now, we can do the same again for tan of A minus B. And we've got two ways of approaching it. First of all, we could work through this again, except with tan of A minus B is the sine of A minus B over the cos of A minus B. Or we could work through it again by making the same replacement as we did before and rewriting this as the tan of A plus minus B. Let's be assured that what it is going to give us, whichever way we do it, is going to be that. And so what we've got now are our 6 addition formulae. Sine of A plus B, sine of A minus B, cos of A plus B, cos of A minus B. These are the ones you must know and learn. From those 4, you can derive these. It's a help if you know them, if you can learn them. The important thing is to be able to recognise them when you see them and recognise when you need to use them. Let's have a look at 3 fairly typical examples of the use of these. In many ways, it's practice that we're getting at recognising these particular formulae, because we may need them more often when we're doing other more complicated manipulations. So first of all, let's have a look at this particular problem. If we know that sine of A is 3/5 and that the cos of B is 5/13, then what's the sine of A plus B? What's the cos of A minus B? Okay. We've got sine A, but we don't know anything about cos A, seemingly. We've got cos B, and we really don't know anything about sine B. We don't know much about A and B, really, because A could be either an obtuse angle or an acute angle. So we really need a little bit more information. So let's say that A and B are acute. In other words, they're both less than 90 degrees. Well, if they're both less than 90 degrees, one of the things we can do is represent the angle and the sine with a right-angled triangle. So let's just have a look at that. Right-angled triangle, right angle there, the angle A. Sine A is 3/5. Opposite over hypotenuse. So that's 3, the side opposite the angle A, and that's 5, the hypotenuse, which is always opposite the right angle, always the longest side. Pythagoras tells us that this other side has to be 4. And so now that we know the adjacent side, we know everything about angle A. We know its sine, we know its cosine, and if we want, we can find its tangent. Let's do the same for the angle B. Here is the angle B in its right-angled triangle. And we're told that cos B is 5/13. Cosine is adjacent over hypotenuse. This is the side that's adjacent, so there's 5. This is the hypotenuse, the longest side, the side opposite the right angle, so that's 13. So using Pythagoras' theorem, this side is 12. Now notice I said using Pythagoras' theorem, But it was as though I knew these. 3, 4, 5, 5, 12, 13. I do know them. And you've got to get to know them as well. Pythagorean triples. Simple triples of integers, whole numbers, that obey Pythagoras' theorem. If you have them at your fingertips, can recall them easily, you'll find this so much better in working in trigonometry, because these numbers are used an awful lot. Okay then, let's have a look at what we can do. Sine of A plus B. The addition formula tells us this is sine A cos B plus cos A sine B equals sine A, we know is 3/5, times cos B. And we know that one, it's 5/13. Plus cos A. We can read cos A off here. It's adjacent over hypotenuse. So it's 4/5. Times by sine B. And we can read sine B off this triangle. It's opposite over hypotenuse. 12/13. Do the arithmetic. 3 5s are 15 and 5 13s are 65. So that's 15/65 plus 4 12s are 48 and 5 13s again are 65. And so that gives me a fraction, 63/65. We had cos of A minus B. So let's approach that in exactly the same way. We'll quote our expansion, our addition formula, cos of A, cos B, plus sine of A, sine of B. Substitute our values. Cos A, that's 4/5, adjacent over hypotenuse, times cos B, that's 5/13, adjacent over hypotenuse, plus sine A, that's opposite over hypotenuse, 3/5, times by sine B, that's 12/13, opposite over hypotenuse. Now, here we've got some fractions, and it might be tempting to cancel the 5s here. 5 goes, 5 goes. But 5 times by 13 is the 65, and 5 times by 13 is the 65 to have the same denominator. So I'm not going to cancel. 4 5s are 20 over 5 13s are 65 plus 3 12s are 36 over that 65 again, giving me 56/65. So that's one way in which these can be used. Let's have a look at another way. Supposing we were asked to find what's sine 75, but no, don't reach for your calculator. You've got to work out sine 75 as an expression, not as a set of decimals, but as an expression. Well, what we've got to think about is how can we make 75 from angles whose sine and cosines we know very well. Well, 45 plus 30 gives us 75. And 45 and 30 are two of the angles that we know sines and cosines for. Exact sines and cosines. So, this would be sine of 45 cos of 30 plus cos of 45 sine of 30. Sine 45, that's 1 over root 2, times by cos 30. Well, cos 30 is root 3 over 2, plus cos of 45 is 1 over root 2, times by sine of 30, which is just a half. So we have root 3, that's 1 times by root 3, over 2 root 2, plus 1 over, and again 2 times root 2 is 2 root 2. We've got the same denominator, so 2 root 2 to root 2, and on the top root 3 plus 1. Now we'll leave that one like that. We might try and get rid of this root 2 in the denominator, but just for the moment, let's leave it like that. There's nothing to be gained by doing it at this stage. And let's take another example. Let's have a look at tan 15. Now, what we need to be able to do is to find 15 in terms of angles that we know lots of things about. And of course, one of the ways of doing this, but only one, is to do 60 minus 45. So that means that we need the addition formula that's to do with tangent and the one that's to do with the tan of a minus b. So this is tan 60 minus tan 45 over 1 plus tan 60 tan 45. So now let's put the numerical values in. Now the tangent of 60 is root 3 and the tangent of 45 is 1 over 1 plus root 3 times by 1. So we'll have root 3 minus 1 over root 3 times by 1 is just root 3 plus 1. Now, that's all right, and it's correct. It doesn't look very nice, and we tend to have a tradition of not leaving things like root 3 plus 1 in the denominator. So one of the ways of tidying that up is to multiply top and bottom of this fraction by the same thing. Multiplying top and bottom by the same thing keeps it the same value. But what should we multiply it by? Well, I'm going to choose to multiply by root 3 minus 1. Not because that's what's in the numerator there, but because this is the difference of two squares, a plus b, a minus b. And a plus b times by a minus b, let's just write that down up here, is a squared minus b squared. So that means that on the bottom I have root 3 times by root 3, a squared, which is just 3 minus b squared. And b was just 1, so that's just minus 1. And 3 minus 1 is 2, an integer, not a surd, not one of these things with a square root sign attached to it. What have we got on top? We've two brackets that we're multiplying together. Root 3 by root 3 is 3. Root 3 by minus 1 is minus root 3. 1 by minus 1 by root 3 is minus root 3, and minus 1 with minus 1 is plus 1. 3 plus 1 is 4 minus 2 root 3's we're taking away, all over 2. And now there's a common factor of 2 on the top and on the bottom. 2 into 4 goes 2, and 2 into minus 2 root 3 goes minus root 3. And 2 into 2 goes 1, so we needn't worry about that one. So there we've got a second example to add to the first one that we did. Let's take one more type of example where we can make use of the addition formulae. And this is where we get to simplify an expression. So supposing we've got the sine of 90 plus a. Could we have this simpler? Could we just have, say, sine a, or minus sine a, or cos a, or something like that? Does it have to be 90 plus a? Well, let's have a look. It's sine of 90 cos of a plus the cos of 90 sine of a. Sine 90 is 1. And cos a is just cos a. So first of all, we have 1 times cos a, which is just cos a. But cos of 90 is 0 times by sine a. Well, anything times by 0 is 0. So we're just left with cos a. So an expression such as sine of 90 plus a reduces to cos a. What about something like the cosine of 180 minus a? Well, this is cos 180 cos a plus sine 180 sine a. The cosine of 180, well, that's minus 1. So minus 1 times by cos a is minus cos a. Sine of 180 is 0, and sine a is just sine a, but 0 times by anything is 0. So we're just left with minus cos a. So we can see that these addition formulae help us to very quickly simplify and get in terms of this angle A, possibly quite complicated expressions. But the basic thing is that these 6 addition formulae, again, I stress it, you have to learn, you have to know, but most importantly, you've got to recognise them and recognise their use when you see them and when you see the situation.